Special relativity. In his Annus Mirabilis, or Miraculous Year of 1905, then non-famous 25-year-old Albert Einstein published 4 papers which revolutionized modern physics, including on the electrodynamics of moving bodies. This paper introduced the world to a new field of physics, special relativity, which explained physics phenomena at velocities close or equal to the speed of light. The foundation of special relativity relies on 2 postulates. The first postulate, also known as the principle of relativity, states, the laws of physics are the same in every inertial frame of reference. Inertial reference frames are reference frames that are not accelerating. The reference frame is not experiencing a net force. A bus moves past a stationary observer with a constant velocity v. Both the bus and the observer are in inertial reference systems. From the stationary observer's perspective, the bus moves forward with a velocity v. From the perspective of a person on the bus, the observer is approaching the bus with a velocity v. Einstein's first postulate states that both observers are correct in their observations, since they're both in inertial reference systems and rely on the same laws of physics in regards to how velocity vectors sum. This postulate applies for all inertial reference frames. A voltage can be found in the coil of wire regardless of whether the magnet approaches the stationary wire coil or the wire coil approaches the stationary magnet. Einstein realized that his principle of relativity applied to Maxwell's equations of electromagnetic radiation as well, which can be used to derive the speed of light. This derivation is relatively complex. Einstein's second postulate states, the speed of light in a vacuum is the same in all inertial reference frames and is independent of the motion of the source. Einstein's second postulate states that the speed of light is invariant. It does not matter what reference frame the observer is in. Light will always be observed traveling at 3 × 10⁸ meters per second in a vacuum. Suppose a rocket moving at 1,000 meters per second launches a missile forward at a speed of 5,000 meters per second with respect to the rocket. An observer on Earth watching the launch would measure the missile's speed to be 6,000 meters per second because it was launched out of the moving rocket. This is what we learned in classical mechanics. If the same rocket sent out a light pulse, the rocket would observe the light pulse traveling away from it at the speed of light, 3 × 10⁸ meters per second. Einstein's second postulate says that an observer on Earth would also observe the speed of the light pulse as 3 × 10⁸ meters per second. Classical mechanics states that an observer on Earth would measure the speed of the light pulse as 3 × 10⁸ meters per second plus 1,000 meters per second, but this is incorrect. The invariance of the speed of light leads to problems with simultaneous events. Time intervals are related by simultaneity, the idea that an event occurs in a definite location in time. 2 events that are simultaneous in one frame of reference are not simultaneous in another reference frame moving relative to the first reference frame, even if both are inertial. Whether or not 2 events at different locations occur simultaneously depends on the state of motion of the observer. Events that are simultaneous in one reference frame are not simultaneous in another. There is no basis for which reference frame is correct. As long as a reference frame is inertial, observations in that reference frame will obey the laws of physics in that frame. Observations in one inertial reference frame may not be the same as observations in another. When observed from a stationary reference frame, like the Earth, the elapsed time in a moving frame, like a spaceship, is less. This difference in elapsed time between the 2 inertial reference systems is called time dilation. The Lorentz factor, gamma, is used to relate the elapsed time in 2 reference frames. It is defined as this equation here, where u is the speed of one reference frame relative to the other, and c is the speed of light. This is not an equation that is on the AP2 equation sheet, and you do not need to know it. Plotting the Lorentz factor as a function of the relative speed of the reference frames shows us that for very low speeds, the Lorentz factor is approximately equal to 1. For low speeds, less than 1/10 the speed of light, relativistic effects can be ignored. Classical mechanics works fine. However, as we get closer to the speed of light, the Lorentz factor grows exponentially. Relativistic effects become much more noticeable as the velocity approaches c. The Lorentz factor is used to relate the time intervals of the two reference frames. Delta t sub p is the elapsed time as measured by an observer where the events take place at the same position. It is known as the proper time interval. For our spaceship example, the proper time interval is measured by the observer in the spaceship. Delta t is the elapsed time in the reference frame moving with respect to the stationary frame, and the events take place at different positions in space. Proper time interval is always the shortest time interval measured. Consider a spaceship moving towards Proxima Centauri, the closest star to the Earth, at nearly the speed of light, which we cannot do. This is theoretical. An observer on Earth measures a longer time interval for the spaceship to get to the star than the navigator on the spaceship due to time dilation. The navigator measures proper time, related to the time measured on Earth, as follows. So we would use this equation to figure out how the time spans differ in the spaceship versus on Earth. Relativity of length. An observer on Earth is at rest relative to both the Earth and Proxima Centauri. The observer measures the distance between Earth and the star as LP, known as proper length. Proper length is the length measured by an observer who is at rest with respect to the two endpoints. Both the Earth observer and the spaceship's navigator agree that the spaceship's speed relative to the Earth v is the same. Solve the velocity equation for distance. Distance equals velocity times time. Since velocity is the same, and time is different for the Earth observer and the spaceship navigator, the distance observed by these two people must be different. The spaceship observer is measuring proper time, as the measurement of time occurs on the navigation deck when the ship starts at Earth and reaches Proxima Centauri. The Earth observer is measuring proper length. The Earth observer starts the clock on Earth and then stops it when the spaceship is at a different position, the star. The Earth observer measures the longest distance, LP, proper length. The spaceship navigator measures the length contraction distance, L. The same observer may not be measuring both proper time and proper length. In the spaceship example, the spaceship navigator measures proper time and contracted length. The Earth observer measures dilated time and proper length. Dilated time is always greater than proper time. Contracted length is always less than proper length. So what do the observers agree on? Assume there are two observers, both in inertial reference frames. If there's no relative motion between them, they agree on everything: time, length, object speed, and speed of light. If they're moving at relative speeds less than approximately 10 to the 7th meters per second, they agree on time, length, and speed of light. However, if they move at a relative speed greater than 10 to the 7th meters per second, they only agree on the speed of light.